Fine-tuning is the most misunderstood word in applied AI. Most people think it means teaching a model new facts. It does not actually. Fine-tuning changes how a model behaves, its tone, its format, its style, far more than what it knows. Over the next few minutes, we go from what fine-tuning really does to LoRA, QLoRA, the tricks that let you train a billion parameter model on a single GPU, and the one decision that matters most: when to fine-tune at all, and when retrieval or a better prompt would actually serve you better. So, what we will do is, in the beginning itself, we will start with what it actually is. A base model has already been trained on huge amounts of text, and its knowledge and behavior lives in billions of numbers called weights. Fine-tuning takes that trained model and continues training it on a smaller, focused sub-dataset of your own examples. The weights shift to fit your examples instead of what it was actually trained on. The key insight is what this is good at. Fine-tuning is excellent at shaping behavior, a consistent format, a specific tone, following your instructions, speaking in your domain's language. It is weak at injecting fresh facts reliably, because facts learned from a few examples are easily forgotten or confused. Behavior, yes, go for fine-tuning. A live knowledge base, no, we have to go for retrieval. So, the original approach is actually called full fine-tuning, where you update every single weight in the model. It works and it is very powerful, but the cost is absolutely brutal. So, when you want to actually train a model with billions of parameters this way, you need to hold the weights, their gradients, and the optimizer state in memory all at once, which can be many times the size of the model itself, which means that heavy VRAM consumption. A model that barely fits on one GPU for inference might need a cluster of them to fully fine-tune. You also get a complete new copy of the model for every single task, tens of GBs each. For most teams, full fine-tuning is simply out of reach. That problem is exactly what the next idea solves. LoRA, low rank adaptation, is the breakthrough that made fine-tuning affordable. So the idea is actually elegant. Freeze the entire base model, change nothing in it, and inject tiny new trainable matrices alongside the existing weights. So what you are doing is, instead of updating a giant weight matrix directly, LoRA learns two small matrices whose products represents the change. Because they are of low rank, they hold a tiny fraction of the parameters, often well under 1%. You train only those, so memory and compute drop dramatically. So this means that the base model always stays untouched, and your entire fine-tune is saved as a smaller adapter file, sometimes just a few MB that snaps on top of the original. QLoRA pushes this further and is why you can fine-tune a large model on a single consumer GPU. So what it does is that it combines two ideas. First, quantize the frozen base model down to 4 bits per weight, shrinking its memory footprint roughly 4 times. Second, train LoRa adapters on top of that quantized base in full precision. So what's happening is the heavy base sits compressed and frozen, while the tiny adapters do the complete learning. The result is actually quite striking. Models that would normally demand a server can be fine-tuned on one card with a fraction of the memory, with very little quality being lost. QLoRA is what put fine-tuning in reach of individual developers. So here is the part that decides everything: your data. So a fine-tune is only as good as the example you feed it. So most fine-tuning today is instruction tuning, where each example is a prompt paired with the ideal response you want the model to produce. The model learns the pattern of your inputs and outputs. The hard truth is that quality beats quantity by a wide margin. A few hundred clean, consistent, correct examples will always outperform tens of thousands of sloppy ones because the model faithfully learns whatever you show it, including your mistakes and inconsistencies. So, garbage in really is garbage out. So, curating this data set is the real work, not running the training. The training itself is the same loop that built the base model, just smaller. Feed in an example, let the model predict the response token by token, compare its output to your target, measure the error, and nudge the trainable weights to actually reduce it. One pass over your whole dataset is an epoch, and you usually run only a few. This is where the biggest danger lives: overfitting. Train too long, and the model memorizes your examples instead of learning the pattern, getting brilliant on your training set and worst at everything else. So, what you do is you watch a validation set to catch this. The goal is to learn the style, then stop before it actually starts parroting. A handful of settings control the outcome. Rank sets the size of the LoRa adapters. Higher rank can actually capture more, but risks overfitting and costs more. While a modest rank is often plenty for this particular fine tuning. Learning rate sets how big each update step is. Too high and the training becomes unstable. Too low and it barely leans. It barely learns basically. Epoch set how many times you pass over the data, and with small data sets, 2 or 3 is often enough. There is also which layers you adapt, commonly the attention projections. You do not need to fine tune all of these at once, but like start with the sensible defaults, change one thing at a time, and let your validation number actually guide you. So now the decision that saves you the most time and money, should you fine tune at all? What you can do is like you have to work up the ladder. First, just improve the prompt, better instructions and a few examples in the context, solve a surprising amount with zero training. Next, if the problem is actually about missing knowledge, your own documents, recent facts, anything that changes, use retrieval, which is RAG. So fine tuning cannot keep up with changing facts, but retrieval can. Reach for fine tuning when the issue is persistent behavior. You need a reliable output format, a specific voice, or a skill that prompting cannot pin down. And you need it without pasting examples every single time. One example would be a cybersecurity analyst. Often the best systems combine a fine tune for behavior with retrieval for knowledge. So once you have made the decision and actually trained it, you have a small adapter, not the whole full model. And that changes how you actually ship it. You can either merge the adapter back into the base to get a single standalone model, simple to deploy, or you can keep it separate and load it on top of the base at runtime, which unlocks something powerful. One base model in memory, but serving many different adapters at once. A single deployment can host a support adapter, a coding adapter, and a summarizer adapter, swapping the tiny files per request while the expensive base is actually shared. That is the operational payoff of LoRa. Cheap to train, cheap to store, and cheap to serve many specializations from one single base model. You can find so many LoRa and QLoRa adapters in Hugging Face itself. So here is the whole picture. Fine-tuning continues training a model on your examples to shape how it behaves, not what it knows. Full fine-tuning updates every single weight and costs a lot of fortune and load of VRAM. LoRa freezes the base and trains tiny adapters instead, and QLoRa quantizes the base model so it fits on a single GPU. Your dataset decides the result, and quality beats quantity every single time. So watch for overfitting, tune a few key knobs, and most importantly, climb the ladder first. Prompt, then retrieval, then fine-tune. Only when the problem is actually about behavior. Get that decision right and you save weeks. No magic, just the right tool for the right job. So I hope I answered how fine tuning actually comes into LLM. If you have any questions, let me know in the comments.